when will the stars go out? In 100 trillion years, the last stars will burn out, and the universe will be dark forever onwards. This is the end of the stelliferous era, and the beginning of the degenerate era, a period of near eternal decay. There's an ocean of time between now and then. The universe as we know it has been around 13.8 billion years. The potential for beauty, complexity, and life will continue for a long, long time. But one day that period will end. Stars, the engines of the universe. By the end of the stelliferous era, stars will have used up their fuel. The process that enabled stars to shine will have led to an inevitable endpoint. No new stars will be born. Stars die when they deplete the fuel in their core. The star's mass compresses and squeezes the core of the star, and in the immense pressure, atoms fuse together. In fusion, two smaller atoms join to become one larger atom, releasing energy. Hundreds of millions of tons of material may fuse every second in a star like our Sun, a small amount of that matter turning into pure energy. Over millions or billions of years, the lighter atoms are used up. Normally, stars fuse hydrogen into helium, but in a star's old age, when its main fuel is depleted, they are forced to compress heavier atoms. Indeed, almost all the matter we see around us was forged in one way or another by stars. The oxygen we breathe came from exploding large stars, while carbon, a key element in all life, was squeezed into existence in dying smaller stars. Only hydrogen and a little bit of helium and lithium condensed out of the chaos of the Big Bang. When a star's fuel is depleted, when fusible material is used up, they either explode or cool off, depending on how big they are. Stars are born in stellar nurseries, dense nebulae, freely floating hydrogen in space. While the amount of hydrogen in any one part of the universe is finite, and the amount of it inevitably decreases over time as stars fuse heavier elements, even 100 trillion years in the future, a lot of this hydrogen remains. It is just too dispersed, too thin and spread out to coalesce into anything substantial. Smaller stars last far, far longer than larger stars. Their final moments may differ dramatically, but 100 trillion years in the future, all stars that will ever have been will have died. The smallest stars simply peter out of fuel. Our star will expand, casting off its upper layers, leaving a hot, dead core. The largest stars collapse and explode, leaving an ultra-dense core, either a neutron star or a black hole. Dead planets will drift in eternal shadow. Extinguished cores of stars will tend towards absolute zero, the coldest temperature possible. Gas will linger dormant. Dark galaxies, or agglomerations of galaxies, will be strewn huge distances from each other, much more distant than they are today. Right now, at the largest scales, the universe is expanding at an ever-increasing rate, thanks to dark energy. Galaxies are pulled apart from each other, and so the matter of our cosmos dilutes away. Long before the end of stars, each galaxy will seem to exist in its own bubble universe. Other galaxies will have moved away so far and so quickly, much faster than the speed of light, that they will never be able to see each other, let alone come into contact. In the far future, any person looking further than their home galaxy will see a dark, empty cosmos. Not because the stars have burnt out, but because the distances between galaxies becomes simply too great. Our own galaxy, and all the stars we can see with the unaided eye, are part of it, will have merged with its neighbours long before. Galaxies very near each other can overcome the expansive force of the universe through their mutual gravity. Between 4 and 5 billion years in the future, the nearest galaxy, Andromeda, will harmlessly collide with ours to become a supergalaxy, sometimes known as Milkdromeda. Our galaxy, the Milky Way, has cannibalized several other galaxies in the past and absorbed their stars. Their unusual orbits give them away. Here, as all across the universe, we see the interplay of two forces at work. that of expansion or dispersion, and that of contraction, its opposite. The Big Bang set off the expansion of the universe. Tiny areas of greater density in the primordial universe had greater gravity, which pulled matter towards it. This precipitated structure in the universe to form: stars embedded in galaxies, galaxies arranged in superclusters englobing vast voids. Planets needed to wait for a generation of stars to die to form. Stars are held in an equilibrium of these two forces: contraction, gravity constantly trying to compress the star inward, powering fusion, and the expansive pressure outward caused by the fusion counteracts the collapse. Squeeze a star and it will press back harder. For larger stars, as the fuel runs out, equilibrium inevitably fails. Contraction will win temporarily, but in turn this will trigger fusion of heavier elements in the greater pressure, causing an even bigger push outward. Our dying sun's upper layers will expand to engulf the inner solar system, while even larger stars can die in tremendous explosions. A supernova. When stars explode, they release material back into the universe, and this material may help form other planets or stars. Indeed, our sun has had 2 generations before it, and the matter cast off our dying sun will end up in more generations down the line. Planet stuff and people stuff are formed of the materials created by and ejected from dying massive stars. Elements vital for life accrue in the universe, raising the chances for life to appear as time goes on. To a point. After the stelliferous era, in the degenerate era, what remains cools and decays. Eventually, the universe is dominated by black holes, the remnants of huge stars where gravity is so strong not even light can overcome it, while the universe continues to expand into infinity. As Stephen Hawking predicted, even the black holes themselves will disperse, evaporate into non-existence. For supermassive black holes like Sagittarius A star in the core of the Milky Way, millions of times the mass of the Sun, it will just take so much time. Words fail to explain how long this is, even in comparison to the length of the stelliferous era. Yeah. Deep under the surface of the Sun, a countdown ticks on. The Sun may seem unchanging and eternal to us, but fusion, the process by which lighter materials are turned into heavier ones, releasing light, means that our star is constantly evolving. Losing a battle, day by day, year by year, eon by eon, until it runs out of fuel and dies. The Sun fuses about 600 million tons of hydrogen every second, or in a year the mass of one of the asteroids or a small moon of Saturn. For every 1,000 tons of hydrogen fused into helium, 7 tons disappears. It is turned into pure energy. Next time you enjoy a sunny day, just remember where that sunlight originates. Our Sun has lost 100 Earths worth of mass to fusion and solar wind over its lifetime. And how long is that anyway? The Sun has been around 4.5 billion years, and it is slightly older than the Earth and the other planets in our solar system. Everything in the solar system coalesced from the same interstellar gas cloud. The Sun has at least one sibling, a star that was formed from the same cloud, although stars tend to drift away from each other in time, so it's quite a distance away. Our Sun is roughly middle-aged, and we can expect it to last another 5 billion years in its so-called main sequence. The Sun is classified as a yellow dwarf, but it is in fact larger and more massive than the majority of stars. There are far more less massive stars out there, the longer-lived and somewhat unimpressive red dwarf stars. But because red dwarfs are so much dimmer than larger stars, they have been historically very difficult to spot, let alone survey. It led astronomers to believe that our Sun is much smaller than others, when in fact the opposite is true. Hence its misleading category name. Astronomy is full of words and phrases that, under later evaluation, don't quite fit, yet we are stuck with them anyway. Primarily mass, and secondarily the presence of materials other than hydrogen and helium in the core, determine the lifespan of our star. Bigger stars are necessarily hotter, and hotter stars tend to be much less stable. Smaller stars are cool, allowing their constituent fuel to fully mix throughout. Heavier elements in the core get in the way of fusion, cooling it and extending the lifespan of the star. The Sun formed by hydrogen collapsing into a central point. Bit by bit, as helium accumulates in the core, 5 billion years from today, the normal fusion of hydrogen will be impossible. At this point, the Sun will enter a new phase, becoming a red giant. It will dramatically increase in size, perhaps engulfing Mercury, Venus, even the Earth. The Sun will first fuse hydrogen surrounding the core, then, in a flash, it will fuse the helium inside the core. Eventually, after 1 billion years or so, most of the matter that makes up the upper layers of the star will be cast off, leaving a supercompacted remnant. Half the mass of the Sun today, but the size of the Earth, a white dwarf so named because of its immense brightness. This remnant of our Sun will cool from 100,000 degrees Kelvin or Celsius, it doesn't really matter what you use, to become a black dwarf. But a white dwarf is dead. No fusion is taking place, its cosmic metabolism has stopped, never to be started again. It will take hundreds of billions of years to cool to become a black dwarf, and the corpse of our Sun, its ashes, if you like, may remain in the universe forever onwards, or at least we think. The further into the distant future we look, our calculations and predictions simply break down. As our knowledge of the universe has expanded as a species, our understanding of the universe in a practical, day-to-day kind of way has contracted. How many stars do we know of? Scientifically, the number has increased by many orders of magnitude over the last few centuries. How many stars can you see in a night sky? If you live in a city, which is going to be the majority of the audience, the number of stars visible will be tiny. Stars play a much smaller part in our everyday life now than they did for our ancestors. We now know there are roughly 100 billion stars in the Milky Way, and roughly that number again of galaxies in the universe. Humans have speculated on the nature of the heavens for all of history, but it wasn't until 1923 that it was accepted that the galaxy we live in is just one of countless others, as Edwin Hubble had observed. As an aside, in 1755, the philosopher Immanuel Kant speculated that other galaxies exist, or island universes as he named them, but the idea didn't catch on. Perhaps serves him right for some of his intensely distasteful views. Sky glow, the brightness of the night sky caused by artificial lights, is a fact of every modern city. Before the invention of the light bulb, a person would expect to see around 3,000 stars on a clear night. Today, you may only be able to see a couple hundred at most. The totality of the lactic smear of the Milky Way is also invisible for many people today. During the 1994 blackout in LA, several people dialed 911, or the local observatory, depending on the source, to report an eerie, giant silvery cloud overhead. What they were reporting was the image of the galaxy as seen from the inside, its bright core and illuminated dust stretching over the dome of the night sky. They had never seen it before. Modern observatories are built far from urban centres to avoid sky glow. The Royal Observatory in Greenwich, built on a hill not far from central London, hasn't observed the sky since the late 40s. But even better located observatories have been tackling a new threat in the last few years, that of low-orbit constellations of satellites, like Starlink. Starlink plans to have over 10,000 such communication satellites, delivering internet access to remote parts of the world. As the satellites streak across the sky, they interfere with observations, leaving bright lines on photographs. With timing and planning, these can be avoided in some cases, but there is an increasing threat to Earth-bound observations. Starlink may be the first, but this issue is only going to increase. So much of this man-made stuff in low Earth orbit poses a risk of prohibiting spaceflight. If one satellite collides with another, or an untracked piece of junk for instance, the resulting debris can be thrown out to hit other satellites. Junk will collide with more junk, on and on until there is nothing left intact. Not only does this wipe out the satellites themselves, but this Kessler syndrome means that the space near Earth would be too dangerous for humans to return to for many years. Stars have always taken an intimate role in culture. Practically, the positions of the stars, until recently, were commonly used for navigation, for telling the time at night, and to predict and preempt the seasons. Polynesians navigated a triangle stretching from Hawaii to Easter Island to New Zealand using predominantly the sun and the stars, the eye and memory. With no mechanical instruments or compasses, and certainly no GPS, the names and positions of over 200 stars were used for such wayfinding. Navies, today as in the past, still teach celestial navigation as, on a clear night, it cannot fail or be manipulated by an enemy. Stars, more often than not, however, hold a deep cultural and symbolic meaning. Stonehenge, Mayan sites, the Egyptian pyramids, even the Christian nativity have strong astronomical links. Constellations of stars, the zodiac and astrology all find stories and patterns in the arrangements of stars from our vantage in the galaxy. Science has shown the stars not to be gods or souls but bodies of plasma, just like our sun, so far away it's impossible to truly comprehend it, and arranged without care. And they are, just like us, impermanent. But what we know today is undoubtedly more accurate. Perhaps we are losing sight of traditionally important mythological and social meanings that we found in the heavens, just as we are literally losing sight of the stars due to light pollution. Now we have a scientific understanding of the stars, and technology is paradoxically distancing us from experiencing the stars. Can we find new meanings in the heavens? An expansion in technology has allowed a small number of people in the world, scientists, engineers, to understand the universe like never before. But has there been a corresponding contraction in something at the same time, in the place stars take in our imagination? Almost everyone has looked up at the night sky with awe. This basic instinct has inspired myth and science alike. When will the stars go out? To be able to answer this question at all is an astounding feat. 100 trillion years hence, the universe will be a dark and lonely place. Humans, whatever happens in the near future, will certainly be gone long before. While we are here, let's keep looking up.